This module talks about integration and its various rules and methods. Definition of integration. Integration is the inverse process of differentiation. The process of finding a function f(x) given its derivative f(x) is known as integration or anti-differentiation. After studying this module, you shall be able to know the concept of integration, the rules and methods for integration, definite integral as area under the curve. Let us commence our module with indefinite integrals. In the equation given below, integration of fx dx is equal to fx plus c, and when f prime x is equal to fx, f is called an indefinite integral of f. As a symbol of an indefinite integral of f, we use the symbol integration fx dx. The symbol f is the integral sign, the function of fx is the integrand, and c is the constant of integration. The dx part of the integral notation indicates that x is the variable of integration. The integral of a function found by integrating it is not unique, unlike the derivative. In fact, there are infinitely many integrals of a function such that any two integrals differ by a constant. Geometrical representation of indefinite integrals. The indefinite integral of a function represents geometrically a family of curves having parallel tangents at the point of intersection with the lines orthogonal to the axis representing the variable of integration. In the figure, y is equal to minus x square plus c represents the family of curves parabolas having parallel tangents at their respective points of intersection P, Q and R with the line x is equal to a orthogonal to the x-axis, x being the variable of integration. Next, we will study definite integrals. Let a and b be two values of x in the domain of fx, which is continuous function in ab, such that b is greater than a. If we substitute these values successively into the right hand side of equation 1 and subtract it, we get fb plus c minus fa minus c, which is equal to fb minus fa. We note that fb minus fa is a specific numerical value free of independent variable x and constant c. This difference is called definite integral of fx from a to b, where a and b are termed as the lower and upper limits of integration respectively. Symbolically, the definite integral is written as integration a to b fx dx is equal to fx b to a, which is equal to fb minus fa. However, if the limits a and b are expressed as a function of t, then the derivative of the definite integral is written as d dt integration at to bt fx dx is equal to fbt into b prime t minus fat into a prime t. Moving on to basic rule of integration. From the knowledge of rules of differentiation and the relationship between differentiation and integration, we can write the following formula for the integration of functions. First, integration of a constant. Integration a dx plus sx plus c, where a and c are constant. 2. Integration of power functions. Integration of xn dx is equal to xn plus 1 divided by n plus 1 plus c, where n is not equal to minus 1. 3. Integration of x raised to the power of minus 1, which is integration of x raised to the power of minus 1 dx is equal to 1 by x dx is equal to log x plus c. Integration of a constant multiple of a function. Integration of a fx dx is equal to a integration fx dx. 5. Integration of the sum or difference of two functions. In bracket fx plus minus gx brackets closed dx is equal to integration fx dx plus minus integration gx into dx. 6. integration of e raised to the power of ax. Integration e raised to the power of ax dx is equal to 1 divided by a the whole into e raised to the power of ax plus c, where a is not equal to 0. 7. Integration of b raised to the power of x. Integration of b raised to the power of x into dx is equal to b raised to the power of x divided by log b plus c. We shall discuss three methods of integration: integration by substitution, integration by parts, integration by partial fractions. Let us first discuss integration by substitution. This method is used when basic rule of integration are not directly applicable. In such cases, the integrand is transformed by suitable substitution of a given variable by a new variable into a form in which basic rules are applicable. The basic idea underlying this method is the use of a function or chain rule. This method is explained through the following example. Example, evaluate integration of 2x squared plus 7 the whole raised to the power of 5 into 4x dx. 1 is equal to integration of 2x squared plus 7 the whole raised to the power of 5 into 4x dx. Putting 2x squared plus 7 equal to u, then 4x into dx is equal to du. Therefore, 1 is equal to integration u raised to the power of 5 du, which is equal to u raised to the power of 5 plus 1 divided by 5 plus 1 plus c, which is equal to 2x squared plus 7 raised to the power of 6 divided by 6 plus c. Example, integration of x squared plus 1 raised to the power of 15 dx. Putting x squared plus 1 equal to t, we have 2x dx equal to dt. Therefore, 1 is equal to half integration t raised to the power of 15 dt, which is equal to half t raised to the power of 16 divided by 16 plus c, which is equal to t16 divided by 16 plus c. Next, we will study integration by parts. The method of integration by parts is based on the product rule of differentiation. We know that if u and v are two functions of x, then duv divided by dx is equal to u dv dx plus v du dx. Integrating both sides with respect to x, we get uv is equal to integration u dv dx into dx plus integration v du dx into dx, or integration u dv is equal to uv minus integration of v du. Let u be equal to fx and dv equal to gx dx. Therefore, du is equal to f prime x dx and v is equal to integration g x dx. Substituting these values in the previous equation, we have integration of fx into gx into dx is equal to fx integration gx into dx minus integration of gx dx into f prime x dx, or integration of fx gx dx is equal to fx integration gx dx minus integration f prime x bracket open integration of gx dx the whole dx. Taking fx as the first and gx as the second function, equation can be stated in words as the integral of the product of two functions is equal to first function into integral of second minus integral of bracket open differential coefficient of first into integral of second bracket closed. Note, to apply this formula, the integrand should be expressible as a product of two functions such that one of them can be easily integrated. This function is taken as the second function. Example, evaluate integration of log x dx. It is equal to 1 is equal to integration log x into dx. Taking log x as the first function and second function, use ILATE rule, that is inverse logarithmic algebraic trigonometric exponential, and by using integration by parts we get I is equal to x log x minus integration of 1 divided by x into x dx, which is equal to x log x minus x plus c is equal to x in bracket open log x minus 1 plus c. Integration of x tan raised to the power of minus 1 x dx. if we take tan raised to the power of minus 1 x as first and x as second function in the above example, then by using integration by part method, which is equal to tan minus 1 x squared divided by 2 minus integration of 1 over 1 plus x squared into x squared by 2 dx, which is equal to x squared by 2 tan inverse x minus half bracket open x minus tan inverse x bracket close plus c. Next we will study integration by partial fractions. This method is used for the integration of rational functions. A rational function f(x) is defined as the ratio of two polynomials, say px divided by qx, where qx is not equal to 0. If the degree of px is less than the degree of qx, then fx is called proper rational function, otherwise it is called an improper rational function. We shall state without proof that every proper rational function can be expressed as a finite sum of partial fractions. If a rational function is improper, it can be expressed as a sum of polynomial which can be easily integrated, and a proper rational function by division of polynomial in the numerator by the polynomial in the denominator. The method of integration by partial fractions is explained through the following example. Example: evaluate integration of x squared plus 1 divided by 2x plus 1 x minus 1 x plus 1 dx. The integrand can be written as x squared plus 1 divided by 2x plus 1 into x minus 1 into x plus 1, which is equal to 1/4 plus 1 divided by 2x plus 1 into minus half minus 1 into minus half plus 1 plus 2 divided by 6 into x plus 1 plus 2 divided by 2 into x plus 1, which is equal to minus 5 divided by 3 bracket open 2x plus 1 plus 1 divided by 3x minus 1 plus 1 divided by x plus 1. Integration of x squared plus 1 divided by 2x plus 1 divided by x minus 1 divided by x plus 1 dx, which is equal to minus 5 divided by 3 integration of 1 divided by 2x plus 1 dx plus 1 by 3 integration of 1 divided by x minus 1 dx plus integration of 1 divided by x plus 1 dx, which is equal to minus 5 by 6 log 2x plus 1 plus 1 3 log x minus 1 plus log x plus 1 plus c, which is equal to 1 by 6 bracket open 2 log x minus 1 plus 6 log x plus 1 minus 5 log 2x plus 1 plus c, which is equal to 1 by 6 log bracket open x minus 1 the whole squared x plus 1 raised to the power of 6 bracket close divided by 2x plus 1 raised to the power of 5 plus c. Example: integration of x minus 1 divided by x plus 1 into x minus 2 dx, which is equal to a x plus 1 plus b divided by x minus 2. Therefore, x minus 1 is equal to a x minus 2 plus b x plus 1, etc. Putting x minus 2 equal to 0 or x is equal to 2 in 2, we get b is equal to 1 by 3. Putting x plus 1 equal to 0 or x equal to minus 1 in 2, we get a is equal to 2 divided by 3. Substituting a and b, we get x minus 1 divided by x plus 1 into x plus 2, which is equal to 2 by 3 into 1 over x plus 1 plus 1 by 3 into 1 over x minus 2, which is equal to integration of x minus 1 divided by x plus 1 into x minus 2 dx, which is equal to 2 by 3 integration of 1 over x plus 1 dx plus 1 over 3 integration of 1 over x minus 2 dx, which is equal to 2 by 3 log x plus 1 plus 1 by 3 log x minus 2 plus c. Now we will study properties of definite integral. If f(x) is continuous and has an integral over the closed interval a b, then we can write 1 integration from a to b f(x) dx is equal to minus integration of b to a f(x) dx. Second, integration of a to a fx dx is equal to 0. Third, integration of a to b fx dx is equal to minus integration of a to c fx dx plus integration of c to b fx dx for all c lying between b and a. That is, c is greater than a and b is greater than c. Fourth, integration a to b k into fx dx is equal to k integration a to b fx d for any scalar k. If fx is continuous and even function over a minus a, then fifth, integration of minus a to a fx dx is equal to 2 integration of 0 to a fx dx. If fx is continuous and an odd function over a minus a, then sixth, integration of minus a to a fx dx is equal to 0. Let us discuss definite integral as an area under the curve. Let y be equal to fx be a continuous function and its curve. Suppose that we want to find the area enclosed by the curve and x-axis between 2 points A and B in the domain. This area can be divided into n strips each with width equal to delta xi, where I is equal to 1, 2, 3 up to n. Two such strips are shown as shaded in the figure. The appropriate area under the curve can be written as the sum of n strips in the interval a, b. We should note here that the smaller the width of each strip, closer will be the sum of the areas of the strips to the actual area. If delta AI denotes the area of the ith strip with width equal to delta xi and height equal to yi is equal to fxi, then the expression for sum of the area of the strips can be written as sigma I varying from 1 to n delta AI should be equal to sigma I raised from 1 to n fxi dxi. We note that n will approach infinity as delta xi tends to 0. Further in the limit, the left hand side of the equation will become equal to integration a to b delta a, where dA is differential of a, the area under the curve and the x-axis between the points A and B. Similarly, the right hand side can be written as integration b to a fx dx. Thus, a is equal to integration b to a fx dx gives the area under the curve y is equal to fx and x axis between the points A and B. Example, find the area bounded by the parabola y squared is equal to 4ax and its lattice rectum. The area of the shaded region needs to be found where A0 is the focus. The curve is symmetrical about x-axis and the required area is MOM prime M. So the required area is equal to 2 area of MONM. This can be found by A is equal to 2 integration from 0 to A 4ax raised to the power of half dx. A is equal to 4a raised to the power of 1 by 2 into 2 divided by 3 a raised to the power of 3 by 2 minus 0. A is equal to 8 divided by 3a square units. Now let us summarize what we have learned. Integration is the inverse process of differentiation. The process of finding a function fx given its derivative fx is known as integration or anti-differentiation. In the equation given below, integration fx dx is equal to fx plus c when f prime x is equal to fx. F is called an indefinite integral of f. The definite integral is written as integration a to b fx dx, which is equal to bracket open fx bracket close b to a, which is equal to fb minus fa. Basic rules of integration are found from the knowledge of rules of differentiation and the relationship between differentiation and integration. There are three methods of integration: integration by substitution, integration by parts, and integration by partial fractions. We also discussed the properties of definite integrals and how they can be used to find the area under the curve.